the others in the class may not have, so I'll put those out too. I guess, yeah, we are now recording. So let me get the slideshow from current slide. Okay, but before we hit this, I think we already did that slide. So yeah, that's what we'll be starting today. Let me go over the weird week it is. Now, my Mondays and Wednesdays today and Wednesday, no problems at all. Office hours, everything just as before. Okay, but tomorrow I have a doctor's appointment at 11 o'clock, which is right at the beginning of my office hours. And it's one of those I couldn't do anything about. I tried to schedule it during spring break week, but he was on spring break, so he couldn't schedule me then. So he only sees patients on Tuesday mornings. So I have to leave, well, I have to be at the clinic to have blood work done an hour before, so I have to be there at 10, and it takes me at least 45 minutes to get there, so I have to leave right at 9:15, which is right after my first class in the morning on tomorrow. So big change there. And since the appointment's at 12, it should be over, at 11, it should be over by 11:20, but I know from the past that usually late morning appointments, they always get a little dragging, and so I'm going to be lucky to get out of there by 12. That's what I'm hoping to be through by 12. Then it takes me another close to 45 minutes to get back here, so I probably won't be in the office until around 12:45, maybe earlier. I hope earlier, but the good guess would be 12:45. It could be later, but hopefully not. And then I have class starting at 1:15. So I only have a half hour of office hours tomorrow, or approximately that. It may be more if they get finished with me sooner. So that's tomorrow's change. On Thursday, we have the Honors and Awards ceremony. Sometime that morning, I've got to check my emails to see exactly the timing on it. A student told me it started at 9, and a faculty member said, no, we have to be there at 9. So I've got to find out exactly which is the case. I remember 9 was in the email, but I don't remember which way it was. So it really doesn't matter much because I'm in class then anyway. It's just whether I have any class or only a half hour of class, but I'll figure that out. But it does mess with the other end of things because if it does start at 9:30, it'll probably go at least until 11:30, and then another 30 minutes to get back here. So on Thursday, I won't be here until around 12 o'clock, and I have to be at the another class at 1:15. So my office hours, rather than 10:45 to 1:15, probably will be sometime around 12. Could be, I doubt if it's going to be much earlier, but it could actually be a little later, depending on when they let us go. Okay. And then Friday. Normally I'm on Birmingham campus 7:45 to 1 o'clock, but this Friday I have a treatment, so I'm going to have to be there be at the clinic from 7:45 until probably 4:30. So no office hours on either campus on Friday. Okay. Next, any questions on anything we've covered up till now? Okay. Now, my mark and memory is we're on in Chapter 13, Calculus of Vector Value Functions, Section 13.2, Calculus of Vector Value Functions, similar name, in fact, identical name, and it's page 698 in my book. I assume that's about the same as yours. Theorem 2 at the top of the page, okay, or near the top of the page. All right, if there are no questions, then here is Theorem 2. Vector value derivatives are computed component-wise. Thank you very much. I don't know what we would do if you couldn't do this. The vector value function, R of t, this is a bold R, so that means it's a vector function of the parameter t, and the components of that are some scalar function, x of t, of that same parameter t. That's the first t, and the k component is some z of t, that vector function, a vector value function, is differentiable if and only if each of these component functions, scalar functions, are also differentiable. Every one of them has to, not just 2 out of 3. Every one. Okay. So in this case, r prime of t, which is the r dt would be the vector, and this is also a vector. R prime is a vector if r is a vector, and its components would be x prime of t, y prime of t, and z prime of t. So just directly, straightforward, hopefully just like you were expecting and hoping they are, and they are. Okay. So let's do a couple of those. Sorry, my throat keeps coming and going. So here's one. What is, get my pen color back again. D by dt of the vector t squared, t cubed, sine t. What would be that derivative? It would be a vector, by the way, because this is a vector. And what would be the components of that derivative vector? Second? 2t, correct. 3t squared, cosine t. Perfect. Okay? How about this one? D by dt. I never used to say that until I was tutoring. Wait, that's not even what I'm right. An Indian guy, good friend of our families. You know, our families are close, and he was doing his. He went back to India to do his undergraduate degree. And when he came home for Christmas or break or something like that, he was having his big comprehensive test, when he went back. And he needed some tutoring in calculus. And, at least in my experience, Indians talk a lot faster than us Southerners do. And so it was dibbity. But I didn't understand him at first, and when I understood what he said, I found myself soon doing it. So d by dt, okay, of cosine t minus 1 e to the 2t. What's the derivative of that function? Second? Negative sine t. And what's the derivative of a constant? 0. To e to the 2t. Perfect. Okay. And then higher order derivatives are defined by repeated differentiations. So r double prime of t, and this is a vector function, so I'll put the arrow over it since I don't like bold, is d by dt of r prime of t. Okay? And r triple prime of t, also a vector function, would be d by dt of r double prime of t. Now, of course, all these are assuming that the previous one was differentiable. Okay, and so on and so on and so on. All right, let's clear. Any questions on that? Pretty straightforward. Let's clear the ink so we can do example 2. Calculate r double prime of t, of 3, I can't read or talk, where r of t is equal to log t ln t t squared. Okay? what you reckon you're going to do first? Okay, so we'll call that r prime of t, since they're using that notation. And what would that be? 1 over t, 1, 2t. Then, okay, that would be r double prime of t. Oh, wait. Rewrite this one as t to the minus 1. Isn't that what 1 over t is? Okay, what would that be then? Negative. To the negative 2. Okay. Next. 0. Next. Two. Okay. And you can rewrite that if you want to, since you wrote the previous one, minus 1 over t squared. So go back to quotient forms if you want to. 0, 2. Now, once you have that, then and only then do you plug in the 3. Don't ever plug in the 3 before you get the derivative you're looking for, because otherwise you're going to get constants and then you'll have the 0 next. So now r double prime of 3 would be what? Okay. Wait. 0. And what? I didn't hear. 2. Got it. Perfect. Okay. And that's exactly what they got. Good for them. Now, next they show the differentiation rules, which we pretty much have been talking about and hitting on. Well, I don't know if we have in this chapter or not, but we did, or you did, well, I don't know how you did your earlier thing, but when you did differentiation, you had the same thing. Assume now that r of t is a vector function, because that's bold. R1 of t is also a vector function. And R2 of t is also a vector function. And they're all three differentiable vector functions, which means all three. Now, in here we're just assuming we're in 3 space. Okay? We could be in 2 space, or we could be in 17 space, but we're not going there. We're basically going to stay in XYZ space. Okay? Or otherwise XY plane. But you could be in abstract 4 space, 8 space, or whatever. Okay, but assume all the functions, we'll assume there are 3 of them, the component functions are differentiable. Okay. The sum rule says that if you have R1 of t plus R2 of t, now, here the assumption is whatever space this was in, that was in the same space. So if this is in 2 space, that's got to be 2 space. If this is 3 space, that's got to be 3 space, and any higher space too. But the sum rule is simply that R1 plus R2 prime is R1 prime of t plus R2 prime of t. In other words, the derivative of the sum is the sum of the derivatives. Just like we had before with scalar functions, it works with vector functions. Only difference is vector functions have to be on the same dimensions. Okay, constant multiple rule. For any constant c, now, I'll say this, but don't get too hung up about it. That c could be any complex number. We're not going to get into imaginaries, but if it were, it works in for them too. Generally, we're going to stay in the real number system. But for any constant c, even if it was complex, c times r prime of t, c times r of t prime, derivative d by dt of c r of t, is pull that c on the outside, as long as it's a constant with no t dependence, pull it out, c times r prime of t. Just like it was before, when there were scalar functions. The product rule, okay? Now this is a little different. little bit different. Okay? For any differentiable scalar valued function f of t, notice no bold here, no arrow on top, and in the r's, whatever they happen to be, vector value function, then d by dt of f of t times r of t, scalar function times a vector function, it would be f times r prime of t plus f prime times r of t. Just like we did the product rule in strictly scalar functions. The thing is, one has to be a scalar, one a vector, or they both to be scalar. But we haven't touched what happens if both are vectors, because we haven't talked about multiplication of vectors. Well, we did, didn't we? In the earlier, multiplication of vector functions. We did in chapter 12, didn't we? Dot products and cross products. We aren't hitting those yet, so don't sweat those yet. And then for chain rule, notice this is sums and differences. This is a product scalar times a vector function. This is a scalar function times a vector function, product rule. And by the way, I was going to say the quotient rule would work too, but we haven't defined what it means to divide by a vector function. So that's why this is left out here. But these are all our good old standbys. Addition, subtractions, multiplication, multiplication. No divisions yet. But remember, another operation you can do with functions is composition of two functions, which you don't do with scalars in general. You do with scalar functions, but not. And when you do that, then that introduces the chain rule. So for any differentiable scalar function, g of t, you could have left the f of t as we did before, d by dt of r of t, the vector function, as taking as its component g of t, the scalar function, would then be chain rule g prime of t times r prime of t, r prime of g of t. Okay? Now, I don't know why the way I learned it, I always take the derivative of the outer function first, r prime of g of t, and then do times g of t, g prime of t. But this book almost always lists the inner derivative first, and then the outer derivative of the inner function without it. Okay. So that's your chain rule with a composite function of a vector function of a scalar. Now, notice we haven't done scalar of a vector. Okay, we haven't even talked about what that is. So that's how we do the chain rule here. Okay. Now, they do have a proof there that's not too difficult. It's just really time consuming. So feel free to take a look at it and work through that. Okay. Let's move on to example 3. Okay. And what I think I'll do is go back here and do it on this slide. Let r of t, vector function r of t, equal t squared 5t 1. And f of t, a scalar function, equal e to the 3t. Calculate first d by dt of, well, they don't put parentheses. I think I would, but I'll do it the way they do. D by dt of f of t, r of t. All right, Marcus is here. Bottom half of the alphabet doing excellently, but the top half not doing at all. Not visibly anyway. Hopefully they'll get here. So let's do it. How do you do d by dt of f of r of t? And the order really doesn't matter. Either order. So give it to me any way you want to, as long as it's correct. Yeah, that's a product rule. Say again. E to the 3t. So you're starting with f of t. Okay. Okay. Now, if you're doing f of t, then you multiply it by the derivative of r of t. If you're doing f prime of t, that's not f prime of t. Not quite. Close, but no cigars. So which are you doing? Say again? You want this to be f of t or f prime of t? F of t. So you got it f of t. Then you have to do this part is r prime of t. Okay, so what would that be? 2t, 5, 0. Plus 3 e to the 3t times t squared 5t1. Perfect. Except we can do a little bit to simplify. What do you think that would involve? Now, there's two ways you can go. I haven't looked to see. I've done it before. I don't remember how the book does it, but I'm trying not to. How would you like to do this to simplify that? Say again?
To simplify it?
Yeah.
Could you distribute?
Do what?
Could you distribute the E3?
Oh, distribute the E. Yeah. That's one way that I was going to suggest you do, so you tell me what to write. Yeah, 2t e to the 3t. That's fine. 5e to the 3t. 0 plus 3t squared e to the 3t. Is that what you said? Fifteen t e to the 3t, 3e to the 3t. Ooh, basically I ran out of room there. Can you simplify it any further? Add the terms together, corresponding terms, and what would you get? I would say 3t squared e to the 3t plus 2t e to the 3t, comma, there's your first component, second component, t, comma, there's your second component, got it. Now, that's certainly one way to do it. But when I look at that, I think, I don't want to write e to the 3t all that many times. It's in every term of every component. So I'm just as happy with e to the 3t on the outside, and then 3t squared plus 2t, comma, 15t plus 5, comma, 3. Now, that's no more correct than the other is, but it sure is a lot shorter. And I am all in favor of that. All right, 3 out of 4, way to go. top person on the alphabet is now the only one missing. But hopefully she'll come in. But usually she's here by now, so not holding out too much hope, though I will still hope. Okay, let's see. Got to find it. Oh, here we go. All right. They do factor out the e to the 3t, but they leave it in each term. So again, in calculus especially, there are so many stinking ways to write these answers perfectly, absolutely correctly. I don't see how a computerized homework system can possibly, I mean, I would have been guessing forever of how to get that right. I would have sworn I must have done something wrong. No, both of these are perfectly correct. But what they did is open it up and put 3t squared plus 2t in parentheses e to the 3t comma 15t plus 5 in parentheses times e to the 3t comma 3e to the 3t. Perfectly correct. But my word, how many different ways could you do it? I like it this way even a little better, okay? Because it's less writing and it does the same thing. But if you wanted them all in there, their way is perfectly fine too. But you could have written the e to the 3t at the front and put parentheses, front, put parentheses, here I would put it afterwards. So there's just a myriad of ways you can write this perfectly correctly. I don't know how in the world they do that on a computerized thing. You have to really be good at guessing which form do they really want. And a lot of times they only give you like 3 chances or 5 chances to get it. And you may be absolutely right every time you write it, and they still tell you your answer's wrong. So I don't know. That's why I don't mess with it. Okay, sorry if y'all are missing that. Sorry about that. Okay, that was the A part. Let's do the B part. Okay? I don't have room to write it here, so I'm going to write. So everybody got the A part? My 2 ways of writing answers plus theirs of writing the answer. So let's do the B part. Probably will regret doing this, but I think it makes more sense to start over from scratch. And I'll do a lot of scratching. Okay. The B part says d by dt of r of f of t. Okay, you tell me what to write down. Say again. I can't hear you. R prime, okay. R prime of f of t. I see where you're going. F prime of t. Now, did you do that for my sake, or is that how you like to do it too? The book usually puts the F prime in front, and I never do, but you make me feel good. Okay, so don't answer the question. I'll pretend you want to do that one. Okay, go ahead. What would this be then? Okay.
Can we just change the letters for the actual function so we can then take the derivative?
Okay. You need to say that one more time.
Can we plug in the functions?
Right.
And then take the derivative?
Okay. Now, that's exactly what I was trying to think through. You tell me the step and I'll do it. What would be your first thing?
is 2t, but then you're replacing the t with the function of f, right?
Okay. Heard, but I couldn't understand.
So r is, the first term is, in r is t squared,
Right.
but you're taking it in terms of the function of f, right? F function.
Okay. And exactly what do you mean? Give me what that means.
So that would be e to the 3t squared.
Exactly. Okay. All right. So basically what you're doing is this. D by dt of, and tell me if this is what you meant. Exactly what you said there, e to the 3t squared, comma, 5e to the 3t, comma, 1. Okay. Yes, that is what you do. Now, tell me what e to the 3t squared is. Another way to write that. E to the 6t, comma, 5e to the 3t, comma, 1. Okay? And we're taking d by dt of that. Okay? So, r prime of f of t would be what? Yeah, use that one.
That would be
6 e to the 6t, comma, 15 e to the 3t, comma, 0. Okay? Times, now did you see something error I just did? That is not a vector. This is just a scalar. I put a vector symbol there for some unknown reason, okay? Just because I had just done it before. What would this be? 3t. Okay, so now we take that and multiply it through here, okay? All right, look at this. Perfect attendance, way to go. She was just holding out for us to keep our anticipation up, but she got here good. Perfect attendance. Way to go, folks. After losing our Wednesday, we wanted to have everybody here. Okay. We're in chapter 13, section 13.2, and we're doing example 3b right now here, somewhere around page 699 in the new text. In yours, I don't know where that would be, but something like that. So now we're multiply that through, and what do we get? 18 to the 9t, very good. 45 e to the what? 6t, 0. I was going to do that one. Okay. Now, all right, we have done it. Let's see what they got. Wait a minute. I somehow think I disagree with them. Okay, let's see. No. By the chain rule, What they got is exactly what we got on next to the last line. 6e to the 6t, 15e to the 3t, 0. Okay? I do not see it. Now maybe I'm missing something. But I don't think so. The R function takes whatever is the first component, and the first component would be f of t squared. Okay, and that's what we did. Second component would be 5 times f of t, and third component would be 1. 5 times e to the 3t times 1. Okay, and then the last component is 1. And then you take the derivative of that, and I do not see how they did it. It looks like to me they stopped one step short. It looks like what they did was take the derivative of t first and then plug in the f of t for t. And no. It's f by the thing. It's r of f of t. And the r function squares whatever the first component is. And the first component is f of t squared. The second one is 5 times f of t, and the third one is 1. So I disagree with them, but I don't know where to go from there. We just disagree. So anyway, sorry, I can't see how they came up with theirs. I think they just missed it. In the old, okay, number 1, in your printing of this edition, did they get the same answer? Wait, what did they have as an answer? Yeah, they got this right here as their answer. Right? In the second edition of the book, or whatever edition that was, yeah, the second edition, De Silva, what do they have this example? It's 3b. Is it what r of t be t squared 5t1? Do you have that problem? It's right here. That one and f of t be that. Okay, and then the b part says d by dt of r of f of t.
That is the answer.
The b part. And this is the answer they have? Yeah. Okay. Maybe I'm totally wrong, but if so, I don't understand what they're doing. I don't see how that can be true. But let's not waste any more time on it. I think the way we did it was right. Okay? Let's move on to Theorem 3. Now we get, notice I said we didn't have our dot products and cross products here. We only had a scalar function times a vector function, not a vector times a vector, because vector times vector, you have to specify what type of multiplication, either a dot product or a cross product. So this time we're going to assume that R of t and R1 of t, it is a vector function. That's bold. I would have put an arrow over it. R2 of t is bold also, so that is a vector function. That both of these are differentiable. Then the dot product, derivatives of dot product, okay, the product rule for this would be d by dt of R1 of t dot R2 of t would be, hopefully just like you would expect, R1 dotted with R2 prime plus R2 dotted with R1 prime, or R1 prime dotted with R2. Doesn't matter, dot product you can do either way. Okay? So that hopefully would be just as you were expecting. Simple product rule for dot products. The cross product, however, you have to be a bit more careful. Okay? And here's what I mean by that. d by dt of R1 of t, a vector function, crossed with R2 of t. You've got to have a vector function at the end. This comes out being a scalar function, because the dot product of two vectors is a scalar, and the dot product of two vectors is a scalar. So you will have a scalar function at the end. This one, you've got to have a vector function at the end. Okay, so what you do is R1 cross R2 prime, plus, this time you can't flip them. It has to be R1 prime cross R2. Okay? And then whatever those vectors are, and this is a vector, that's a vector, then you can add them together like a function. Okay? And you've got to keep the order rigid. And the dot product, it doesn't matter which one of these you list first or second, and this first or second. Here, it doesn't matter whether you put this here or this there, but you can't flip these, because the cross product does matter, dot product, the order doesn't matter. Make sense? Okay. So, and they do have a proof here. Again, it's not a difficult proof, it just takes a lot of writing. So, in order to move on, we'll do. In the next example, and throughout this chapter, all vector value functions are assumed differentiable unless otherwise noted. So let's do example 4. I don't have a slide for it, so let's do it on this slide. Prove the formula. Do we really want to? Yeah, we can do this. d by dt of, well, let me put the same notation they do. I like to put brackets, they like parentheses. Of R of t, see, you wind up having two parentheses right against each other here, cross R prime of t, okay. They claim, and this is what we're trying to prove, that this is R of t cross R double prime of t. Doesn't quite seem like that would be fair, does it? Okay? But let's do the left-hand side and see what we get. What would we get? That first one. Okay, you're going to start with R prime, that's fine. R prime of t cross R prime of t plus, I'm going to put that in brackets, okay, plus R of t cross R double prime of t. Okay. Now, the second term there matches exactly the right-hand side. What in the world happens to the first term? Okay. The cross product of any two parallel vectors zero. Because remember, the other definition for a cross product, the magnitude of that cross product is the magnitude of R prime times the magnitude of R prime times the sine of the angle in between. And since the angle in between, they're the same vectors, the angle in between them is zero. Sine of zero is zero. So that term is zero. For that reason, do you see? So this term is zero. Because they're the same vectors, but it would work for any two parallel or anti-parallel vectors. If they're exactly in the same, well, exactly in opposite directions, that too would be zero because the sine of 180 or pi is also zero. Okay, so that's why it's true. Sure enough, the second term is equal to the right-hand side. Any questions on that? They say because the cross vector of a vector with itself is zero. That's the same thing Emmanuel said. All right. Now, the next little section talks about the derivative vector R prime as a tangent vector. That's not too big of a stretch either, is it? The derivative vector R prime of t0 at some specific point t0 has an important geometric property. It points in the direction of the tangent to the path traced by R of t at t is equal to t0. To understand why, consider the difference quotient where delta R is R of t0 plus h minus R of t0, and the delta t is equal to h. That's your change of independent variable is h, where h is not equal to 0. And I think they have this next slide there. Yes, they do. So this is what your delta R over delta t would be. Change of R would be R of t0 plus h minus R of t0. That's your delta R, change of two R's, slight difference apart, divided by the change of t, your independent variable, which would be t0 plus h minus t0. The t0's go out, and that just leaves you h. So yeah, there's your difference quotient. And that's the thing we're taking the derivative of, okay? And as h approaches, the limit of that as h is approaching 0, okay? Now, if you think about this, R of t0, let's just imagine you have a function here, and R of t0 would be that function, going from here to that point here. And t0 plus h is going over here, so R of t0 plus h would be this function. What's the difference in those two? That would be a little vector in this direction, because this one plus that would give that. Yeah, okay? So that's in the direction of motion of R along whatever path that was going. If R of t plus R of t0 is here and R of t0 h is back here, that would be the direction that would be going. So yeah, that would be your that little vector difference between those two vectors. My arm waving is not very good. Let's see. Whoa. Let's see the curves first, and then we'll come back. Remind me to come back and do the conclusion, because I did the conclusion before they did the curves. Here's your function line. That's R of t as it's going along. And here's R of t0. At that time, t0. At some later time, t0 plus h, you've moved up to here. Your difference between this one minus that one would be this one here. In other words, this one plus that one equals that one, of course. And blah, blah, blah. Okay. So that would be true there. Now, h then was a very small number, which usually it would be, then to divide that by that very small number is actually going to magnify this vector here. This is the actual difference, but then when you divide it by, or multiply it by 1 over h, if h is a small number, that's multiplied by a fairly big number, so that would be your vector there. The difference quotient points in the direction of r, and r, of course, r of t is here, r of t0 is here, so it's got to point in that direction. If r of t was here, r of t0 was here, it would be pointing in this direction. Okay, so it points in the direction of increase in r as t gets larger. Okay, going from t0 to c0 plus h, where h is some positive value. Okay, so there's your, what those two show you. Now what we're going to do is let that h get smaller and smaller and smaller, approaching 0. And I can't get all three of these on here, so I'll get the first two alone and then do the third one. So this is the, from the last one, r of t, 0 minus r of t, that would be your difference here divided by a small number, that gives you your vector there. Parallel to this one, in fact, along this vector, but with 1 over h being less than 1, your h being less than 1, 1 over h is greater than 1, so it extends that. Okay? Now, let that h get smaller. Okay? Bring it in a little bit, and bring in a little bit more, and a little bit more, and you see that h is getting smaller. The difference here is getting smaller, but the h is also getting smaller. So hopefully we got a indeterminate situation there. So you are coming and approaching some limit. Okay? And sure enough, by the time you get the h approaching 0, then you're approaching the tangent vector, because as you get closer and closer, that secant vector here becomes a shorter secant vector, closer to the curve, becomes a shorter and shorter and shorter until it is a tangent vector directly along the curve. And h is approaching 0. And they show the magnitude not really changing much. It could be changing. I don't know what it's doing. But you see it's an indeterminate situation. The delta r is getting smaller, but the h is getting smaller too, and hopefully that limit does exist, and whatever the magnitude of that is, that would be that limit. Does that make sense? Same way we did derivatives before, but this time they're vector functions, not just scalar functions. Okay, so we go back to this. You're supposed to remind me, but I remembered. Okay. So the tangent line at r of t0 and this L here, in this book, see, I'm teaching Cal 1 from a much earlier chapter. I think we're somewhere back around chapter 4 now. And this one, they use the L, that capital L, for a lot of different things. Okay, that was the linearization. This is very similar to the linearization, except this is actually a line. The tangent line is a function of t, would be the r of t0, that's the place it's starting from, plus your parameterization t in the direction of r prime of t. So that's going to be your scalar that multiplies that. And this looks a lot like basically a slope-intercept form. Y is equal to mx or mt plus b. It's not quite, because you don't have y-intercepts and other things like this, but it really does take on that form. And that would be your tangent line, the equation of the tangent line, at any point r of t0. You just calculate the derivative of that point and the value of the function of that point and add the t times that derivative there. Got Okay, I think that puts us ready for example 5. All right, and believe it or not, this is the graph of that, which I don't even want to think of drawing myself. Okay, I'm glad they drew it. Plotting tangent vectors. Okay, now let's see, there's a couple of notes here. Let's see if they're of any importance. Although it has been our convention to regard all vectors as based at the origin, the tangent vector r prime of t is an exception. Visualize it as the vector based at the terminal point of r of t. This makes sense because r prime of t then appears as a vector tangent to the curve. Yeah, we've been doing that, and I think without really raising any concerns at all. So I'm going to say, why bring it up if it's not a crucial issue? Anyway, here we go. Plot r of t, and here's your r of t. Thank goodness they're doing the first part for us. And this is a vector function. First component, cosine t. Second component, sine t. Third component, 4 cosine squared t. Okay. It says plot that vector function together with its tangent vectors at t is equal to pi fourths and 3/2 pi. Okay. Find a parameterization of the tangent line at t is equal to pi fourths. We'll do a parameterization here. Okay. So they want plots for the function. Okay. Tangent vector at those 2 points and a parameterization of the tangent line at the first of those 2 points. Okay? So, they say plot it. I say, oh, I don't want to. Okay. Here is their rendition of the plot. Let's see if it kind of makes sense. Okay? Now, first thing to note here is their strange orientation. If you don't notice this, you'll probably get pretty confused. Here's their x coming this way, their y going back that way, and the z going up. That's still a right-hand rule system, so it's perfectly fine. But usually you put x's down here and y's over here. Not in this case. They've chosen to write it this way. And you can orient it any way you want to as long as it's a right-hand system. And this is. Okay? So, when t is equal to 0, your x coordinate is what's cosine of 0? Cosine of 0. Cosine of 0. 1. Okay, so you come out x1. Your sine of 0 is 0, so your y is not going anywhere on y. And then 4 times cosine squared. Okay, let's first, cosine of 0 is 1. Square 1 is 1. Multiply by 4, and you got 4. So you're up here at this peak right here. 1 this way, 4 that way. Now, it doesn't look to me that their scales are very even, because if that's 1, that looks like less than 2. So it looks like they compressed the z-scale somewhat. Can't say for sure. Anyway, that's where we start. T equals 0 starting right up there. Let's do t is equal to pi halves. Cosine of pi halves is 0, so x is 0. You're somewhere along the y-axis, at least to begin with. Sine of pi halves is 1, so you're out there. And 4 times cosine of pi halves is, of course, 0. Cosine squared would be 0. 4 times 0 is 0. Therefore, you are at pi halves. You start at pi halves, 3 has pi back here, basically the same as we had before, but 3 has pi cosine, which is the x-coordinate is -1, this is 0. No, that's not right. Yeah, the y is 0, you don't move right or left, and then this is 4 again. And why the 4 back here is taller than the 4 here, it's a thing of a slant coming forward. I'm glad they drew it, not me, but I don't like the drawing much anyway. Okay? And then you come on around, t is equal to 3 has pi, cosine of 3 has pi, cosine of any half pi is 0, sine of 3 has pi is now -1, so you're -1 here. So you're +1 here and -1 to the other. Again, it doesn't look like you're spacing it very nicely, but okay. And then cosine 3 has pi is 0, square that is 0, 4 times 0 is 0, so there you are, and then you go back up here. So that's what you trace. Now, I want to ask you a question that has nothing really much to do with this problem. Certainly not what they're asking in the problem. What's the horizontal trace of that curve? This has to do with what you were doing before. What's the horizontal trace of that curve? In other words, if you projected downward, had a very bright light at infinity on Z, projected downward, what would be the shadow of this curve on the xy plane? In other words, ignore the Z variable. It's always 0. What does that give you on the xy plane? That's MT sine t. Say again? Okay. Not a line. A what? Not a point. A circle, exactly. Because, and it's a unit circle in fact, right? It just goes round and round and round a unit circle. So looking at this from above, that would be tracing a circle. Now, on here it would look like an oval because of the way you were trying to draw a three-dimensional figure in 2 dimensions. So, but that's exactly what it would be. It would be a circle. Here it went to +1, +1, -1, -1. Yeah, that's a circle. That would be the horizontal face of that curve. And then the z's go up and down like that. Okay. I guess the other question, what would be the either of your 2 vertical traces? I'll regret asking this one. That would be, starts at 1, 0, goes up to 0, 4, and comes down to, oh wait, I'm sorry. Starts at 1, 0, up to 0, 4, and down to -1, 0. That would be half an ellipse, I think. Can't think of any other way to describe it. And this way, you would be from 4 -1, 4 down to 0, 0, and up to +1, 4. I don't know. I think that probably is half an ellipse also, but like that, not closing, But that's beside the point. That was trivial we don't need to do. Okay. So that's sort of the plot. We agree with their plot. I don't like the way they oriented it, but we're okay. Here we go. So they plotted for us, thank you very much, R of t. And we agree. Together with the tangent vectors that t is equal to pi fourths. If t is equal to 0 is this point up here, and t is equal to pi halves is down there, pi fourths is somewhere in here, and that would be in the going this way and projecting upward. Off of that circle, upward, right there, remember this is a circle on the horizontal trace, and from that point on the circle there, where x and y are equal, because sine of pi fourths and cosine of pi fourths are both square root of 2 over 2. So at that point there, project upward, and there you have it, t is equal to pi fourths. Okay? Now, they are showing the tangent line there. Now, my first glance thought that was pointing straight down, but it's not quite, because you see this is straight down, this is not quite. It's pointing a little this way, and sure enough, it has to be bending inward, because you're yes. Oh, that, yeah, okay, right.
Hammer was in office, and we just looked to see if this.
That's it, okay, thanks.
We tried to go over there this afternoon, but for sure it won't.
Okay, oh, so you don't have to pass over there today?
Not today, I don't.
Okay, well, don't take a special trip. I can run by on the way home. Because he's probably not going to be there when you go by, is he?
Well, like I said, I usually try to go in the afternoon, just a matter of fact.
Oh, you do try to get, okay, right.
Class over there, so.
Okay, yeah, well, then
I'll
you,
get everything I need to get taken care of, and I usually try to go there just to meet with some students and honor students and stuff like that.
okay, well, if you're going anywhere, I didn't want you to make a special trip.
But it's
Saturday.
next weekend.
Oh, that's true, isn't it?
Yeah.
Yeah, okay.
So I just want to make sure this is
That
right.
is
next
correct,
weekend.
yeah, next week.
Okay.
That gives me a free weekend. Oh, yeah, it would be Easter weekend.
Yeah, right.
Yeah, right. Well, yeah. Thanks. Sorry about that. That's, by the way, the science march. If any of you are interested in doing, I think it's 10 to 2. He just took a poster at Lynn Park, downtown Birmingham. And it should be quite a nice crowd. So, anyway. So this line is not parallel to the z-axis, I don't think. Looks like this is wider here than it is down there, especially than it is down there. So it's not. It is coming. It doesn't. It's just something that doesn't look right about it to me. I don't know. It has to be. Does it have to be pointing toward the circle there? I don't think it does. But anyway, that's the tangent line, just along that curve, going in that direction. Okay? The next one is far easier. If t is equal to 3 halves pi, remember 3 halves pi, this might answer our question here too. This would be, at pi fourths, this would be square root of 2 over 2, square root of 2 over 2. So it has to be on that bisecting line, the identity function line that goes right, cuts that in two, okay? And then when t is equal to pi fourths, cosine is square root of 2 over 2 squared, that would be 2 over 4, which would be 1/2, and 1/2 of 4 would be 2. So that sure doesn't look like it's in the right place, does it? If this is 4 up here, 2 looks like it would be lower than that. But it's okay. I mean, I'm not drawing it, they are. And it is curving inward because this is as far out as it goes going that way. So the curve is in this way, and perhaps a little, no, it would have to be moving out that way because this is y is equal to 0 to this, so it's on the x-axis it's going towards 0, not directly towards 0, but towards 0. Toward the y-axis this way, but from the from x, it's going that way because it's moving out. And like I said, illustrating something three-dimensional on a two-dimensional plane is really hard to do. There's a tangent line, approximately. Now, tangent vector. At 2/3 pi, why do I not have that blown up? Be easier to do, but I'm glad all of you are here. I feel bad when I talk to the board and I realize people at home can't see what I'm pointing at, but you're all here, so you do know what I'm pointing at. As I was saying, at this point, it's moving that way on y, okay, because here y was 0, there's y is 1. Up here, x is 0, here x is y, so it's coming this way on x and that way on y. And I'm not convinced I understand their projection there, but it's okay. But on this one, pi 3 has pi, that's easy. This is -1. No, this is 0. X is 0, and of course it is. Y is -1, and sure enough, that's at -1 over here. And this would be at 0 again. Yeah, 0 and z. So, its motion here, it has no z component, okay? Not because it's z here, but because it was going down in z, then it's going up in z, so it must have a 0 component in z here. There's negative here, positive here, it has to be 0 there. And it must be going parallel to the x-axis this way, okay? Because it's increasing in x and reached its maximum here, it's going to start decreasing. So it was moving this way, it will be moving that way. So this must be 0 in this direction, you know, or parallel to this in that direction, and no y component. Okay. So sure enough, there's your tangent vector here. Now, why they drew this one to be so large here and this so short here, does that make sense? Well, I guess maybe so. This is at a place where you have the largest change coming up, so that may be close to your maximum velocity, you might say, along the curve. And here it's basically changing directions in 2 dimensions, in the z and in the y dimension. So it's that's probably a minimum there. So I wouldn't be surprised if it wasn't. So I guess that's a fair rendition. So there we've drawn they've drawn the 2 vectors, but we agree with them. Now it says find a parameterization for the tangent line at t is equal to pi fourths. Okay, the one up there, the little more difficult one. Will you tell me what the parameterization of that tangent line would be? They use the term L of t. Now they said L of x, but we're going to use t. I think they said L of x, didn't they? No, they use L of t. Okay? Just the equation just above example 5. What would that be? You read it to me. Hint. It's that. Okay? You see it right above example 5? So what would that be? R at t0 plus t times r prime at t0. Now in this problem, what's our t0? Pi fourths, right? That's the one they're asking for. At t is equal to pi fourths. Okay? So our L of pi fourths, no, L of t. Okay, sorry. T0 is pi fourths. T is your variable. Don't mess with your variable. It's t, okay? So this L of t is equal to, now what is your R at pi fourths? Well, let's do it. R, we've done it verbally. But you tell me again. What would that be? Cosine of pi fourths? A little louder. Over 2. Yeah. Square root of 2 over 2. What's sine of pi for us? The square root of 2 over 2. Yeah. Okay. And as we said before, the cosine of square root of 2 over 2, when you square that, you get 2 over 4, which is 1/2. And 1/2 of 4 is 2. Okay. So there's your r of pi fourths, or r of t0. So that's going to be root 2 over 2, comma, root 2 over 2, comma, 2. They like their 2's, don't they? Plus t. T is your parameter. Don't plug in anything for that. That's your parameter here. Now, r prime at t0. We first got to figure out what r prime is. So you tell me what r prime is at t. Here's your r of t. Yes, the x component is negative sine of t, comma, cosine t, comma, okay, very good. I like to do it this way, and you don't have to do it. 2 times 4 is 8. Cosine t, that's the first part. Then chain rule it, and that gives you your negative sine t. Okay? You were probably getting there, weren't you? Okay, kind of. Moving sort of in that direction. So there's your r prime of t, but now we want that r prime at t0, which is pi fourths. And that's going to be square root of 2 over 2, comma, square root of 2 over 2, comma, let's go and write them out. Negative 8 times root 2 over 2, comma, oh wait, no, times root 2 over 2. Since I've got something there, let me do this. Okay? Now, second? Yeah, okay. These two multiply to be 2, so that wipes one of those out. That goes into that 4 times. So you're absolutely right, negative 4. Okay? Why did I stop writing up there? Oh, here's why, because that's what I put in there. Minus root 2 over 2, root 2 over 2, negative 4. Negative 4, okay. Got it. Okay? So here is your parameterization for this line. L of t is equal to, now frankly, you could leave it in exactly that form, and I'm beginning to say, why change a thing? But you could write it this way, and I think sometimes they do. Root 2 over 2 minus root 2 over 2t, comma, root 2 over 2 plus root, I'm going to put the t in front. T, or I should have put it on the other one too. T root 2 over 2, because I just like to have the variable in front of the radical sign so I don't confuse myself and think the t's under the radical, comma, and this next one's pretty easy, 2 minus 4t. Okay. I really can't think of anything to improve that. Let's see what weird form they write it down as. they left it in exactly the form we had before. That one up there. Root 2 over 2, comma root 2 over 2, comma 2, plus t times minus root 2 over 2, root 2 over 2, minus 4. Okay. Now, they do say something here. There are some important differences between vector and scalar value derivatives. The tangent line to a plane curve, y is equal to f of x, where f of x is a scalar function, is horizontal at x0 exactly when f prime of x0 is 0. But in a vector parameterization, the tangent vector r prime of t0 equal x prime at t0, comma y prime at t0 is horizontal and non-zero if y prime of t0 is 0, but x prime of t0 is not 0. Okay. You need to think about that a little bit. I don't think it's a real major thing. They made it sound like it was going to be, but it really doesn't matter. Imagining the case where a vector value function r of t describes a particle moving along a curve, it occurs when r prime of t is equal to 0, r prime of t0 is equal to 0. The particle has momentarily stopped its forward motion. It can be subsequently continue to move forward or move in any other direction from that point, including reversing itself and returning along the path on which it arrived. We'll see this phenomenon in the next example, which will be a perfectly good one. All right, here we go. Here's the function r of t. They like that name, don't they? R of t. Sort of the f of t of vector functions is r of t. Okay? And this is the vector function, two-dimensional vector function, t minus sine t, comma, 1 minus cosine t. And this is what we call a cycloid. Okay? And it says find the points where A, r prime of t, is horizontal and non-zero. R prime of t is equal to, I probably should do this, is horizontal and not equal to 0. Okay? The B part will be where r prime of t is the 0 vector. We'll get to that a little later. So, how are we going to do this? You tell me where to begin. Help me, help me. Where do we begin? At least in this portion of most chapters like this, when there's a question like that, where do we begin? Quite often, 9 out of 10 times, your answer is going to be take a derivative, of course. Okay, so let's do that. That's what we're looking for, where it's horizontal, so let's do r prime of t. And what would that be? It's going to be a vector. 1. Cosine t, comma, put minus a minus, sine t. Okay, there's your first derivative. Okay? Now, what they say we wanted to do, where that is horizontal. Now, what's going to be true about the horizontal part of it? So what's going to be 0? Of what? Of both? Both components? Now they drew the graph for us, which is helpful. That's a cycle. Keeps on going. Now they showed this for t's only positive, so we'll live with that. But what we want is where the dy dx is equal to 0, right? Y being the vertical component. And the dy, that's where the sine t is equal to 0. And, or is it? No, the horizontal part is equal to 0. It's not changing, sorry. Where this is equal to 0. And where is that? No, where is that right? Where the horizontal, where r prime is horizontal, okay? And where is the horizontal? That's when the y is not changing. So yeah, it's the y part. And where is sine t equal to 0? You tell me. 0, pi, 2 pi, 3 pi, n pi, right? Okay. But we also want to know where it's 0, but the vector itself is not 0. So let's consider those values. When t is equal to 0, what is 1 minus cosine 0? Say again? Yeah, but we'll start with 0. Is 0, so the x would be 0. So this one would not fit this bill. Okay, because then it would be 0. Is it time? Is that what you were saying? How could it be? On the odd pies, okay? On the even pies, this is also going, wait, is that? Yeah, okay. Because on the odd pies, this will be 1 minus a minus 1, which would be 2. Okay, so the x component's not going to be 0 there, but the x component's going to be 0 on the even pies. So on the even pies, it's going to be the b part, and on the odd pies, it's going to be this part. Okay, so we've answered it. We didn't do a probably good job of writing it. Look at that in the book. We'll start next time at example 7 on page 701. Okay, homework exercises here. We came close to finishing, didn't quite make it. Homework exercises here. Do any of the odds 1 through 5, any of the odds 7 through 11. Do either 13 or 15 or both, you choose. Do any of the odds either 17 or 19 or both, you choose. Do 21. Do any of the odds either 23 or 25 or both. Do 27. Do any of the odds 29 to 33. And let's see. Let's stop somewhere about there. We'll pick up the rest of those later. Now, did everyone here get a copy of the test that was on chapter 12? All except for the 12.6, because that's in the test with this one. Everybody got it? Good deal. All right, we will see you on Wednesday.